Good morning. We will continue factor analysis. Today our discussion will be on two issues. First one is model estimation, then followed by model adequacy testing. Both related to exploratory factor analysis. Both related to these two. Now, what we have seen in last class, that the exploratory factor model is this: lambda f plus delta, and the variance structure is like this: sigma equal to lambda transpose plus psi. Okay, this one is P cross P matrix, this is P cross M, this one is M cross P, and this one is P cross P diagonal matrix. Okay. By estimation, what we mean to say, we want to estimate lambda. The estimate of lambda is lambda cap. We want to estimate psi, that's psi cap. So we can say, now what is known to us? We know that is capital sigma cap. This one we can assume as S. This is also P cross P matrix. So then, how do I go about for estimating these two? One is P plus M, P cross M vector, another one is P plus P cross P vector, but where this error term or specific variance term is diagonal. Okay. So essentially, suppose you have collected a data N cross P matrix, this on P variables, Px variables basically related to x, and you have computed S also P cross P. Now, if we think that the sample size is large and sampling strategy is appropriate, then we can say that the sigma estimate, which is basically sigma 1 sigma 1 2, like sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, like this, sigma 1 p, sigma 2 p, sigma p p. These estimates, which is basically S, where S is S11, S12, S1p, S12, S22, S2p, like this, S1p, S2p, SPP. Correct? So these are the estimates which in general, if I say sigma jk, that estimate is sjk for j equal to 1 to p, k equal to 1 to p. Now, we can assume that under a good estimation, that what will happen ultimately, if our sampling size is appropriate, adequate, and we are able to capture properly the behavior, covariance structure, so that sigma jk equal to sjk. That means, what I mean to say here, I mean to say that each of the element in capital sigma and this S, this will be very close, very close. So, we have P cross P matrix here, and number of estimating parameters will be here half into P into P plus 1 into P. This many parameters, because if you see the structure here, you see this portion is mirror image of this. So, ultimately if it is not this P cross P, it is other than this value. Okay. That means essentially what we are estimating here, or what we are assuming here, we are assuming that we want to estimate something that is sigma, which is lambda cap lambda transpose plus psi transpose. That is what we want to do. Basically, using these estimates, we want to find out these values, estimate of these values. So, other way what we will do, we also do not know this one, we know S only. So, we initialize values for this lambda cap and psi cap, and then we find out this value. Then we compare this value with S, individual elements of the vector, and we find out a situation where the difference between element of these two matrices will be as small as possible within certain threshold limit. But what is in factor analysis, what you will find out that the variable each variable variance is a key issue. So, when we talk about stress of this is nothing but the sum total of j equal to 1 to p sum total of sigma jj, that means the variance of each of the sum total of variance of each of the variables. That means similarly, if I say stress of S, that is also j equal to 1 to p S jj. So, instead of then we require what we require a function to be minimized. Now, if we go for the least square estimates, squares estimation, then what you will find out that we require to minimize the error. What is error here? The error is the difference between the two. Okay. So, our sample covariance matrix is this, population covariance matrix is this, and we want the minimization function which basically minimize the sum square errors, that means sum square of the elements of this matrix. Here we will consider, as we are interested in the variance component, we are considering here that sum square error like this, and for so this is in the matrix domain. So, this will be like this will be this, and then we take basically we minimize a function related with g, which is trace of this. Okay. So, essentially this leads to that norm, second norm, this we can say instead of S, if we write lambda transpose plus epsilon plus psi. So, this is what is sigma. Okay. So, we want to minimize this function, So, what are the thing you must know? See, if you want to minimize, then you take the derivative that by maximum derivative of this, and then with respect to the parameters put it into 0, and then you get this value. This is the standard way, general way we used to do when we have the very simple functions. Here there are problem is that you will find out that your lambda, capital lambda as well as psi, these are the unknown parameters. Okay. If I take with respect to lambda, and what is required here, we require to know, particularly we have to initialize the values. So, as a result, what is required, we require an initial estimate of psi. Initial estimate of psi, this is one. The second requirement is how many factors we are extracting, m factors. What is this value? Value of m. That value also you require to know. Essentially, if we look into the factor model, number of parameters to be estimated as well as that what is the degrees of freedom available, then what we will find out? We find out that the degree of freedom is number of parameters for that capital sigma. This is unconstrained, and minus number of parameters for sigma constraint. Okay. In the unconstrained case, the total number of parameter will be half p into p plus 1, and when you make a constant case, that is pm plus p minus half m into m minus 1, and this will lead to half of p minus m square p plus m. Okay. So, this is what is the degrees of freedom available. Now, if your degrees of freedom DOF is 0, you will get a unique solution. If DOF greater than 0, you have several solutions. So, and if DOF less than 0, it is not determined. So, we can say the factor model is indeterminate. Okay. The general situation is this. This is the general situation. So, what we want, as we will be getting large number of solutions, because there is no unique solution in this case and it is overestimation situation. So, you require to put certain constants. Okay. That constant will be lambda, that psi inverse lambda, this transpose this will become 0. So, this will become, if this becomes 0, this will become diagonal. This become diagonal. That is the constant. This one is m cross p, this is p cross p, this one is p cross m. So, resultant will be m cross m. So, ultimately the diagonal elements, m elements will be there, and of diagonal elements that will become 0, and as a result you will find out that this is the number of parameter you are relaxing, you are basically fixing to 0, and ultimately you are getting this. Okay, that is what is we are saying about. So, you have to fix that m in such a manner that your degrees of freedom should not be this, as well as we don't want also this, we want this situation. Now, with this what I can say, with this background, I will now explain what are the methods available for estimations. First one is principal component method. Second one is principal factor method. And third one is your maximum likelihood method. Okay. First we describe principal component method. It is similar, it is basically what we have done in PCA. In PCA, you have considered the population covariance matrix, and we say that this one is can be decomposed. This can be decomposed into its eigenvalue and eigenvector pairs. Eigenvalue and eigenvector pairs. Okay. Actually, if I say that Qj is the eigenvalue and Ej is the eigenvector, in then what you can write? You can write that sigma is Qj, Ej, suppose Ej we are writing like this will be P cross 1. So, Ej transpose then summation of j equal to 1 to P. This is known as spectral decomposition. Okay. In PCA, when we described this, we instead of Qj, I have written this as lambda j, but in this case we are using lambda, that capital lambda, which is the component lambda 1, these are the factor loadings. So, I am using Qj for eigenvalue. If this is the case, then can we not proceed like this, that this is my Qj, Q1 E1, E1 transpose plus Q2 E2, E2 transpose, like this, QP EP, EP transpose. You can write like this one in this manner. So, similarly, this can be written Q1 root E1, Q2 root E2, Qm root Em, then Qp root Ep, multiplied by root Q1 E1 transpose, root Q2 E2 transpose, like root Qm Em transpose, root Qp Ep transpose. Okay. So, if we denote this first portion as lambda, then this will definitely lambda transpose. Okay. So, that means essentially we are writing that sigma is lambda, lambda transpose. and it is possible. You can verify this, it is very much possible. And in this case what is happening here, so there are P, so number of components extracted is P, and your this matrix is also P cross P matrix. So maximum possible component is extracted, and here definitely we are assuming that the rank of this matrix is definitely P, that is full rank, okay, in this sense. But in factor analysis, what is the purpose? Purpose that there are many variables which are correlated. So in that case we want much less number of factors, that is M, where M is less than P. So in that case, if I say that this is the domain of our M and similarly this much is for another M, then the remaining portion we can attribute to the error terms or specific variance, because if we do not extract P factors, which we also do not want, we want a subset of P that may be very small. If M equal to 1, that is the best, if M equal to 2, 3 or like this, but it must be the subset of this. So we are now making little manipulation here. What we are saying that I want to write that sigma equal to this transpose plus psi, where this delta 1 is nothing but we are considering q1 e1 root q2 u2, so ultimately root qm em, that we are considering. So that means remaining portion means root over q m plus 1 e m plus 1 to your qp and ep, this portion we will this portion multiplied by its transpose we will relate to this psi. Okay. If this is the case, then I can say that my first factor, if it is f1, okay, this factor is loading is root over q1 and u1, where u1 is the eigen vectors, which is u11, u12. So how many variables are there? P variables, P cross 1. So for factor 2, it will be root q2 e2. I am talking about the loading part. So similarly, your factor m, this is qm em. Once you have this values, but how do you get these values? These values will be got, you will use S matrix, that is the sample covariance matrix, which then will write this lambda cap transpose plus psi cap. Okay. So in this case your things will be like this, all will be cap, E1 cap, E2 cap, EM cap. Fine. So using S, you will estimate this lambda, then, and that is through spectral decomposition of this S matrix. You will do the spectral decomposition S matrix, and then how do we get the psi? Psi you will be getting equal to S minus lambda cap transpose. Then what are the steps? Steps are find, suppose first step is find S, second step find out eigenvalues and eigenvectors of S. Okay. Then third one is you select M, and then fourth one is once you select M, then find out the loading, so obtain lambda, that is lambda cap. Then fifth one is obtain psi cap. So how do you select M? It's a tricky one, but there are certain suggestions. So if you, because you see this equation, you are interested to find out this value. So this value is nothing but lambda cap transpose is nothing but S minus psi. What is this rank of this? Rank of, what I mean to say, find out the rank of this matrix. But you don't know psi. Here the way we are giving, you are basically finding out to this psi. So if you go by this method initially, you first find out this one. There are methods to first select the number of factors that we will discuss. Okay, but if you initialize sigma cap as sigma 0 cap, then you find out this one, find out this rank. Or if we also, you can find out that what is this rank of this matrix, and then you can start with. But this principal component analysis, once you get like this, then using the eigenvalues, you can find out that how many factors you will keep. That you have seen in PCA. There are different methods of keeping the identifying the number of principal component to be kept. For example, that cumulative percentage, for example, your average eigenvalues, for example, the broken stick method, for example, your scree plot, for example, we have also gone for certain hypothesis testing there also. Okay. So those issues I will under model adequacy test I will explain a little bit more, but at present we will see that using AS and principal component analysis or principal component method, how the factors can be retained. Let us take one example here. Suppose my S is this 100, 50, minus 30, 50, 64, minus 20, minus 30, minus 20, 49. It is a 3 cross 3 matrix. What I want? I want let M equal to 1 factor model. So what does it signify M equal to 1 factor model? That means there is one factor, let it be F1. I have 3 variables x1, x2, x3. I want to extract one factor out of these 3 variables, and I want to know lambda 1, lambda 2, lambda 3, and also there is delta 1, delta 2 and delta 3. Fine. And essentially the factor model, all of you know this. If we use S, this will be lambda transpose plus psi if we use cap. This is the situation. Okay. Now here our lambda cap is 3 p cross m, that means it is lambda cap 3 cross 1, and you will find out, it is obvious, this is lambda 11 estimate, lambda 21 estimate, lambda 31 estimate. So we want this. In addition, we want psi cap, which will be your some value here, psi 1 cap, psi 2 cap, psi 3 cap. This will be 0 0 0, then 0 0. We want this. We want this from this data using principal component analysis. So I will not go for obtaining, means I am not going for deriving that how that principal components analysis is done to find out this eigenvalues and eigenvectors. That we will not describe here. Straight away I am going to give you the results, because it is 3 by 3 matrix, computation will take time. So all of you know that Q I, determinant of S minus Q I, that will be 0. In PCA analysis I written like this, S minus lambda I equal to 0. Here I am using Q I told you earlier, because to differentiate lambda as loading, not the eigen values. So if you do like this, ultimately it is 3 by 3 matrix. So you will be getting a characteristic equation here, which will be 3 or third order polynomial. So your roots will be Q1, Q2 and Q3, and these values are 148.23, 36.00, 28.70. Okay. So now if you want to know U1 cap, what you require to do, you require to put lambda 1 into the, not lambda 1, that Q1 into this equation, then make this equal to 0. Okay. So our first step is find S is given. Second set is find eigenvalues, these are the eigenvalues, then find out the eigenvectors. So you put this and subject to U1 transpose U1, this equal to 1. So similarly for E2 second eigenvector, you find out like this, Q2I E2, this equal to 0, subject to E2 transpose E2 equal to 1, and similarly for E3 cap, you will be finding out S minus Q3I E3 equal to 0, E3 transpose E3, this will be 1. If you solve this equation, you will be getting this. Solve these equations, you will be getting this. When you solve this equation, you will be getting this. So what are the values for your U1? We have solved. U1 values are minus 0.77, minus 0.54, 0.34. So if you write like this, U1 cap, E2 cap 0.21, 0.29, 0.93, and E3 cap is 0.60, minus 0.79, 0.11. Okay. So what I want lambda 1, which will be basically a vector lambda 1 1, lambda 2 1, lambda 3 1. And you have seen earlier also. Similarly, you can find out here lambda 2, which will be lambda 2 1 2 3. So lambda 1 2, lambda 2 2, then lambda 3 2. Using this lambda 3, lambda 1 3, lambda 2 3, lambda 3 3. Our question is, we want m equal to 1 factor model. So we are concentrating only on lambda 1, not the other two. These effects we are basically giving to the psi, and we are saying that the other two, this 1 factor is sufficient. Okay, so then lambda 1 estimate, what we have said, this is Q1 E1 estimate. So what is our Q1? Q1, I think we found out 148.23. Okay. And what is our E1 estimate? E1 estimate is minus 0.77, minus 0.54, 0.34. So if you multiply these two, what you will be getting? You will be getting minus 9.37, minus 6.57, 4.75. Okay. So this is your this lambda value. Now what you want, I think if you go by the steps, I said select m equal to 1, obtain sigma, that is lambda cap, then obtain lambda cap means you are basically here lambda cap is this one. So you have obtained lambda cap. Now what you require to know, you have to find out or obtain psi cap. In order to obtain psi cap, you require to know what is lambda cap transpose. This value will be minus 9.57, minus 6.57, 4.75 into its transpose, minus 9.57, 6.57, 4.75. The values are, when we estimate this into this, this into this, this into this, like this. So ultimately you will be getting 87.80, 61.56, minus 44.51. How do we get this? 9.57 into 9.57 is this, minus 9.57 minus this one, this, minus this plus this minus is coming, that is the way. So I repeat again, minus this into minus this is this, minus this, this. So in the same manner, this cross this cross this cross this, you will be getting values like 61.56, 43.16, minus 31.21, then minus 44.51, minus 31.21, 22.56. So your psi cap is S minus lambda cap transpose, which is 100, 50, minus 30, 50, 64 minus 20 minus 30 minus 20 49 minus this matrix minus this matrix. So, ultimately you will be getting a matrix like this. So, off diagonal element we want 0, there is quite large values. Now, how this value is, how much large, that to be tested, but by just seeing these simple values we may not be able to judge it, that it's whether it is significantly large or not, it is difficult. Okay. So, in order to, so this is what is our principal component method, PC method. Now, second method is principal factor method. I think we have discussed somewhere. A second method is principal factor method. In the first method, the principal component method, what we have done, we have basically taken this matrix, or you can say that estimate of this matrix. Basically, when you are talking in sample domain, we are talking about this matrix, and our aim was to extract as minimum number of significant factors, and that what is this minimum value that we have not discussed, I will show you. But in principal component analysis you have seen that what are the important factors, that components that can be kept. Okay. So, in principal factor, that factoring case, what we will do, you take any value x, that is the variable, any variable xj. This variable variability is sigma jj. Okay. And we have seen in last class that this can be partitioned into two halves. One is psi jj, which is unexplained or specific variance, and then other one is this. Hj square. So, this one is communality, this is your specific variance. Now, if we, and also you have seen that your sigma is lambda transpose plus psi, or S, when you have written you can write S this plus psi. So, that means this into this, that is lambda into lambda transpose is S minus psi. Okay. So, instead of S matrix, if we now factorize S minus psi matrix, that means we are not taking this one, we are basically considering the communality, that is the common variance explained by the factors. Clear? So, whatever the method we have adopted so far, that means we have seen that principal component. So, in principal component you found decomposed S in PCA based PCA method. Here what we are saying, we use this decomposed S minus psi. Now, if you do little more manipulation here, so our my S is this S11, S12, S1P 2P. And if I say my psi is okay, so I create S minus psi means the diagonal elements will be changed. Okay, now using this, now what is happening here, we are writing that sigma jj equal to hj square plus psi jj. Now if we take the estimate, that means sjj equal to hj square plus psi jj, then sjj minus psi jj equal to hj square. So you are writing here h1 square h12 1p h12 h2 square h2p 1p 2p h, that is hp square. Now you factorize this. So again, if we can say, suppose the eigenvalue and eigenvector pair like this, suppose q star, if you say q star and e star, or qj star ej star j equal to 1 to p, you will be getting exactly the same thing what we have done in PCA using S. Or just now what we have developed, that spectral decomposition of S, in the same manner you have to find out. Okay. So in this case, if I say that lambda star estimate, as we are using this star and this one, so this will be nothing but your root estimate q star, that one u1 star estimate, q2 star estimate, e2 star estimate. How many you are interested? Suppose qm star estimate. So you can go up to p, but essentially what will happen, that when there is correlated structure, this matrix you will find out much less than p, maybe the rank will be less than p, that is one, that you have to test it. Otherwise also, that p minus m, these factors which we are not considering, they will have much less that contribution in explaining the variability of the x variables. Okay. So this is the second method, but please keep in mind that in the second method case, that you are factorizing s minus psi, you know the value of s, but you don't know the value of psi. So you have to initialize this psi, so you have to find out this psi 0, and initialization, one of the initialization I told you that delta means it will be iterative procedure, please keep in mind this one, iterative procedure. You initialize, then find estimate, then again you see that what is the size coming, and then psi that matrix can be acceptable or not, what is the variance explained, what is not explained. Then again you go on repeating these things, and finally some convergence will take place, and then you will be able to accept that model, if at all that model is to be accepted. Okay. So I think the third method, what we are saying, that the third one is third one is our this one, what I said, that third one will be your maximum likelihood. Maximum likelihood method. This is really complicated one. What it is required, that you have to find out the likelihood function. Getting the likelihood function is not easy thing, but you have to find out this. So see what we have discussed here. We discussed here that maximum likelihood principal component method we have already discussed, that is related to principal component analysis and principal factor analysis. Then there is maximum likelihood estimation. Here I want to tell you one example that is taken from Johnson and Wichen book. Last class we have discussed that 0.44, 0.35, 0.41, 0.35, these are the basically the correlation coefficient values which are more than 0.3. So when more than 0.3 correlation coefficient is there, you can go for factor analysis, that is the suggested one, but that number should be large, that in the sense many of the correlation coefficient will be more than this. Then using principal component factor analysis for two factors, you will be getting something like this factor 1 and factor 2. And if you sum up the squares of these values across the rows for a particular column, you will be getting what you will be getting, you will be getting percentage that the lambda value, or other way I can say that is the eigenvalues, not lambda value, we are talking about q here, q value. Similarly for this, if you square, you will be getting the second q value, that eigenvalue. So, and if you square these values and take sum across basically your for each row, then you will be getting the commonalities. Getting me? So what I mean to say here, I mean to say that when you are doing factor analysis and finding out, suppose this is x1, x2, then xp, then your f1, f2, like this fm, then you will be getting lambda values here. So lambda 1, lambda 2, 1, like this lambda p1. So then when you take that lambda that j equal to 1 to p, so 1 1 1 1 j1 square, this is nothing but your q1 what we have developed. Similarly the second one, j equal to 1 to p lambda 2j, not 2j, j2, that will be your q2. So eigenvalue, here also eigenvalue. And similarly if you take sum here, that lambda 1 1, this is lambda 1 2, this is lambda 1 m, that if I say this is also j equal to, let it be k equal to 1 to m, then your lambda 1 k square, this is what is your h1 square commonality. And similarly like this. Okay. So this is what is estimation. I think I will give you a little inputs to the maximum likelihood estimation, but in maximum likelihood estimation the assumption is xi is multivariate normal, NP, that mu and sigma. So we can say that is NP mu sigma is this plus psi, that is the estimation, and definitely it is for I equal to 1 to n. You will be collecting n observations. Okay. So, the maximum likelihood that we can find out that log likelihood. So, we will first find out maximum likelihood, then the log likelihood of x given mu and sigma. This will be the simplified form will be like this: log of 2 n pi minus n by 2 stress of this minus n by 2 x bar minus mu, this sigma inverse x bar minus mu transpose. Okay. Now, what will happen when you estimate mu cap is as x bar? If you put here, this will become 0. So, then your this likelihood mu cap sigma, this will be minus log 2 n pi n by 2 stress this sigma inverse this. Now, if we say that sigma cap is lambda cap transpose plus psi cap, and then this function will become this cap equal to minus n by 2 log 2 n pi minus n by 2. So, 2 n pi we have written here log 2 pi sigma. I have written wrongly here, that is log 2 pi sigma, then log 2 pi sigma, then log 2 pi sigma. This one you change. So, I will change this one to like this minus n by 2 log of that determinant of 2 pi delta cap psi cap plus stress of, if we are using this, that sense we are writing in it. This type big formulation is there, and Lawley has given some formulation for this, which I will write further. That what Lawley has given, the simplified normal equation by Lawley 1940. He says given some normal equation for solving S psi inverse lambda cap equal to lambda cap I plus lambda cap transpose psi inverse lambda cap, and definitely psi is a diagonal matrix of this is the issue. So, now you have to find out how to solve it, because this is not a closed form solution. You require iterative procedure, and then you will be able to solve this problem. Okay. So, these are the different estimations, and as I told you that this estimation, particularly principal component analysis method, is easy to understand, because you are just decomposing the matrix using spectral decomposition, and in case of principal factor method, that psi value, if it is not known, then you cannot go for that method, but it should be initialized. The initialized point is that if you can take the diagonal element of S, that also possible. You take the diagonal element of S initial value, then you repeat this process. and in maximum likelihood estimation, that is probably this is preferable one, because there are a lot of statistical tests which are possible, but it is the derivation point of view, it is a little difficult. And as an applied engineer or a scientist, what you require to know? You require to know the basics, the useful formulas, and how to use all those formulas when data is given to you. Okay. So, what I have tried to give you certain basics, but not the way the statistician will give you, because that is not my cup of tea also. Then final one, I think that another 1 minute of time, what I want to complete, that you have to do certain test, that is what I can say model adequacy test. I will explain you that Bartlett test here. Okay. Here the step 1, step 1, step 2, step 3, different steps are there, but I think time is up now. What I will do next class, I will start explaining the hypothesis test, that Bartlett test, and then we will go for factor rotation, then factor scores, then followed by one simple case I will show you, so that whatever the theoretical portion I have discussed here, it will be easier for you to grasp. Okay, thank you very much.